Arun sir, are you telling something? Your voice is not coming.
No, I'm just starting. Kish.
Okay, okay, okay. I know
Yeah.
you are moving the cursor, so I thought some problem.
Yeah. See, I just wanted to check whether it is being live streamed. So I
Okay.
wanted to open YouTube and see whether it really happens, but I'm just hoping it is being streamed. I
Yeah,
just,
it is showing live. Maybe it's streaming. I don't know.
yeah. Okay. Okay. So I hope, let's get started. Yeah, so it's an end-term revision session. So when I try to prepare slides for this, so it is really exhaustive, right? So I just try to focus on some important concepts from each weeks. That doesn't mean we only focus on those weeks. So if you have any doubts in a particular week contents, you just pause me there and ask your doubts. Then we move on to the next week. So this is an idea. Okay. I hope you all get it. Okay, so yeah, so the first week we talked much about history of deep learning. Uh, you need not to memorize anything about the history, so there won't be any questions from history. That is for sure. So in fact, everything in starts from this McCullough-Pitts neuron. Okay, so this is a very basic neuron. So we have discussed about this a lot in the lecture, but here I just summarize the important things. Okay, so no matter which neuron we talk about, it always has two components. One is linear combination of inputs, and then passing the output through some nonlinear function. So McCullough with MP neuron is mostly, you can see that all the inputs are taking only either 0 or 1, and it could be minus 1 1. So if it is specified, you can take it, consider it as minus 1 1. If it is not, you can think of it as 0 and 1. So it always takes binary values and combines them and produces some output, and the output is also a binary value. And oftentimes we set a threshold. For MP neuron, the threshold is simply summing up the inputs, and based on the function we try to implement, we set the threshold value. Of course, the output has to be 1 or 0 or 1 or minus 1. So you have to be really careful whether we explicitly mention the output is 1 or minus 1 or 1 or 0. So that is one thing that you need to pay attention. And we know that it implements the linearly separable Boolean function, meaning that we can find if the function is linearly separable, especially Boolean functions, we can find theta that separates the Boolean function, meaning that we can find the decision bounded. And one important difference between this MP neuron and the perceptron is that we don't use weights here. Okay, so MP neurons has no learning in it. These thresholds are set manually. That is one important difference. But it is not, I mean, we follow this difference because some authors associate weights with MP neuron as well, but we follow this one. And we always say MP neuron doesn't have any weights, whereas perceptron has some weights. Since we don't have any weights, we really don't need to tune anything. Okay, so the learning happens in tuning the weights. So for perceptron, we set the threshold manually, of course, by solving set of equations. And the perceptrons is an MP neuron, enhanced version of MP neuron. So there we introduce weights for each input, and these weights are learnable. And of course, now we are taking linear combination of inputs instead of just summing the inputs. Now we are taking a linear combination. And once again, whenever we give explicit equation, right, in exam, most often we mention the thresholding conditions. It's so like equations like this. So you really need to pay attention to this, the index of summation. So what is the starting value, whether it is from 0 to n or 1 to n. Some all these things are, I mean, it makes difference in the answer. So always pay the formula given to you. Okay, it might differ from the lecture. It is not necessarily from the lecture as is. We might simply modify it according to the problem. And of course, yeah, so we introduced the weights and everything remains same. And since we introduced weights, we need an algorithm that learn learns the values for these weights. Okay, so there are a lot of derivations. We don't need to focus on derivations, so we need to actually focus on the final formula. Everything is fine so far, right? You can respond in the chat or
Yes, okay.
Yes.
Okay. And one more, some minor differences are like now the inputs are allowed to take real values, whereas in the previous case, inputs are either 0 or 1, that is binary value. Now it can take both input and output can take real values. Yeah, and the perceptron learning algorithm is really simple. You need not to even memorize this. So you can think of like this. We have data points which belongs to two groups. One is positive and the another one is negative, and we use this formula to decide whether a point. Of course, you have to use the formula given in the exam, but in this case we use this formula to decide whether a point belongs to a positive class or negative class. And here we can see that if I evaluate this summation, if it is less than 0, it means the point belongs to negative class. Okay, so the point actually belongs to the positive class, but my my model says that it belongs to negative point. So which means it makes a misclassification. So since the point is positive, it's a kind of what to say. How do you remember the formula correctly? Okay, so since my point is positive, what I need to do is I have to add my point. Okay, so somehow it is related. It is positive, so you add it because the symbol is positive. Okay, so this is wrong way of giving you how to remember the formula, but I heard that, right? So in quiz 1, some of you said even if you make a mistake, instead of adding the data point to the weight, if you subtract it, you will get a different answer. So it doesn't mean you didn't. I mean, you don't understand perceptron. You are not able to remember it. So it should not, hinder your or hamper your learning process, or should not kind of reduce your mark unnecessarily. So that's why you try to come up with your own way of remembering different formulas. So if the formula or if the formulas are really complicated to remember, right? So we explicitly mention it in the paper. Say, like if you ask you some questions from LSTM cells, we know that it is too hard to remember everything about LSTM, especially those formulas. So in such a case, we give you the formula. We just check you whether you understand the formula itself. Okay. Yeah. So coming back to this, we can see that if my data point is positive, but the model says it is negative, you have to change the weight. So you simply add it. And the other hand, if your data point is actually negative, but your model says it is positive, so in such a case, since it is negative, you simply subtract it. Okay, so it's a kind of straightforward way of remembering this formula. Of course, there are some intricate details in derivation, but you need not to bother about them much. So as I mentioned in the group, if you are able to solve graded assignment questions and practice questions, that is more than enough for the examination. So all those graded assignments and practice questions explore the main concepts covered in a particular week. So once you are able to get a good grasp on those concepts, then that is way better. I mean, you need not to even, if you don't cover something in that particular assignments, you can simply ignore it. Okay. Then we know that we have a perceptron, and perceptron can also only solve these linearly separable data points. So if we if we have a network of perceptron, then we claim that it can solve non-linearly separable data points as well, meaning that some Boolean functions like XOR are not linearly separable. But if we use network of perceptron, it is possible to separate those points as well. Okay, of course, the decision boundary no longer be line; it will be something different. Okay, and there are some theorems which says how many number of neurons should be there in a hidden layer for a given input, number of inputs. Okay, but one takeaway is Of course, I'm just highlighting this one here, but wherever you see this necessary and sufficient condition, you always remember those. Okay, so because that is very, very important. So what do we mean by not necessary but sufficient? Here we are simply saying we need 2n neurons in order to, represent any. Say, for example, if my n is equal to 2, then I have some 2 power 2 power n functions and different functions. So if I want to represent all those functions, how many number of neurons should be there in the hidden layer? So if we say 2 power n, it means 2 power n can be more than necessary. Okay, I can represent a particular function with number of neurons that is less than 2 power n as well. Okay, so that is what implied by this statement, not necessary but sufficient. So there are, I think, only few such statements in the lectures. Except this perceptron, I noticed them. I think, if I remember correctly, in optimization algorithms. Okay, so whenever you encounter such statements, make a note of it. Okay. So from network of perceptrons, and then we really move to a sigmoid neuron. And of course, once you understand the perceptron structure, then sigmoid neuron is nothing different from that. So only thing is that, so instead of using threshold logic, we simply replace it by, or you call this as a step functions sometimes. Okay, you replace it by a sigmoid functions. And when we say sigmoid, in general, sigmoid means it could be logistic function or tanh function, anything that represents kind of S shape. Okay, so when we say logistic, okay, we mean this formula. Okay, when we generally say sigmoid, in the question paper, we try to highlight, I mean, try to mention which function we are actually trying to, we are asking you to follow. So when we say logistic, it's clear you have to use this formula. So when we say sigmoid, I think we don't use this. If we use this word sigmoid, we also mention whether it is logistic or tanh. But most often it is going to be logistic. Okay. But in the exam, we mention this explicitly. So you need not to worry about that. Even if we forgot to mention, okay, if we just said the word sigmoid, but forgot to mention whether it is logistic or tanh, you can pick anything because the mistake is on us. So you don't need to bother, I mean, give your thought on this, whether it is tanh or logistic. You just move ahead. Don't stick with that question for a long time. Okay. Okay. Now the difference is, yeah, so the important difference is threshold logic is not differentiable, whereas sigmoid function is a continuous and differentiable function at, especially at the point of discontinuity. Okay, so the why we want for this, continuity in the nonlinear activation function or continuous function is because the learning itself depends on this. I mean, this we differentiate this function to compute the gradient, so it has to be differentiable. So sometimes people call this as differentiable programming for this reason, because everything is kind of computing the gradients. And from this sigmoid neuron onwards, the entire subject, I would say, once you understand how the learning happens for this single neuron, single sigmoid neuron, then we build everything on top of this single concept, right? So you focus on this, and yeah, so for every model we have these training data points, and also we have this training objective. Maybe we use means square error loss, and in most of the questions we are explicitly mentioned which loss you have to use. Even if we mention mean square error loss, we explicitly give you the formula, whether it is 1 by 2 or 1 by n, whatever that is required. Okay, so we have some data points, and we have some loss function, and also we have some neurons with particular activation function. So the entire learning happens through this weight update rule. Okay, so one of the most, or a cornerstone of this, or if you want to take away one formula, yeah, Samdeep Singh, so you raised your hand.
Yeah, sir, sorry to ask late, but there are some questions in week 1 GA which mentions to identify the inputs whether inhibitory or excitatory. So how to identify those? Like I didn't get the working of it.
Okay, so you are asking a specific question from the graded assignments, right?
Yeah, it is for it is for inhibitory inputs. Like
Okay.
what are those inputs?
So you are asking me what do you mean? I mean, what do you mean by these inhibitory inputs, right?
Yeah,
Or you
yeah.
know what is okay. So in MP neuron, okay, so we use these inhibitory inputs only in MP neurons, okay, where we have some inputs, and of course we follow some logic. We set some threshold, right? And the output is either 1 or 0 based on the threshold we set. Inhibitory means that I haven't for only for MP neuron, not for perceptron, not for sigmoid or any other neurons, only for MP neurons. So if we mention a neuron also takes in inhibitory inputs, okay, meaning that no matter what my non-inhibitory inputs, okay, no matter what their values are, once if we set the inhibitory input value to 1, okay, so the entire logic goes off, the output is always going to be 0. Okay, so which means you are completely turning off the neuron by enabling this inhibitory input.
Okay, sir.
And in graded assignment question, if I remember currently, how do you, I mean, we are saying what the inhibitory input actually does, but how do you implement this inhibitory input? So if that is the question, in one graded assignments, we actually ask you to identify the formula that also considers this inhibitory inputs. Okay, but the logic is this. Once you set this to 1, then the output becomes 0, no matter what the remaining inputs are.
Okay, sir. Got it.
Okay. Okay. So one of the important formula in the entire deep learning is this weight update rule. Okay, so the gradient descent based weight update rule. And of course, I hope you all are aware of how it works. So we have current weight, oftentimes it is an initialized to some random values. Then we compute the gradient of loss function. Of course, we use this notation, and recall that whenever we use this notation, we are actually meaning that we compute the gradient of loss function with respect to the weight W. Okay, so we ignored this additional, symbol or this letter. So it is always going to be, no matter where you encounter, whether it is single neuron or a fully connected network or connet or resonant, it doesn't matter. Whichever neuron you pick up, you have to compute the gradient, and the gradient is always with respect to the final scalar valued function, that is loss function. Okay, and we always have this learning rate. We either set this learning rate to 1, or this learning rate could be adaptive, and this adaptiveness is based on two logic. Either you can explicitly adapt the learning rate by following some rules, or you can tie up this learning rate with the history of gradients. Okay, so every idea emerges from these two rules. No, sorry, not two rules, it's actually a single rule. Here we have weight and bias, so we explicitly written the rules for these two weights. Okay, and the only thing that we keep doing in this entire course is how do we compute these gradients. Okay, so for single neuron it is straightforward, but I really want to give you some insights, given that we explored ANN, CNN, RNN. There is a pattern, there is always a pattern. Okay, so how the gradients actually flows across the entire network. So let's ignore this symbol for the moment. So the grade, no matter which weight you pick up in the entire network, okay, you can see a pattern. So my gradient computation starts from the output layer, especially the loss function. You can see that this quantity here is actually dou y hat. Okay, meaning that gradient, I mean the derivation of loss function with respect to the output layer. Okay, here it is a single neuron, but no, if we have n number of neurons in the output layer, it is not going to change. Okay, so the takeaway is we compute the gradient with respect to the output layer, and then we pass it to the next layer, okay, in the previous layer. So if you look at here, we pass it through f of xi into, in this case, since we are using explicitly sigmoid, so it is going to be sigma of xi into 1 minus sigma of xi. Okay, so if I have some let's say this is my output layer, okay, and then I sum up, I mean I compute the loss here, and then I take gradient of loss with respect to y hat. Okay, say let's say the output we always denote it by y hat. Then I first, once I compute this quantity, okay, in this for single neuron it is a scalar, but if I have some n number of neurons in the output layer, then it is going to be a vector. And then what happens next, right? I have some layers behind it. Okay, so somehow I have to somehow I have to pass this. Why it is keep appearing? Yeah, I have to pass this gradients to the next layer. Okay, all the way up to the input layer. Okay, so how I have this quantity computed this quantity. So in order to pass this to the next layer, first I have to cross this activation layer. So all neurons are composed of two components. One is this linear combination, the other one is the activation. So first I have to cross this activation function. Okay, so I am using a sigmoid neuron here. So the derivative of the sigmoid is simply sigma of x into 1 minus sigma of x. Then I am multiplying this quantity, right, that I computed at the output layer. I simply passing it through the derivative of the sigmoid. Okay, so it's you can think it of as a gate. So these values, these gradients are passing through these gates first. So this is my entry level. Okay, once it passes through this one, of course here we directly encounter the input x, but in the neural network we have this a1 h1 a2 h2 all these things. Okay, but this entire pattern remains same. Okay, so that is what I try to keep on keep you to think about. We have so many common patterns, we have so many dots, but they are all somehow connected. If you keep working out if you keep solving the problems, you can figure out all these patterns. Okay, of course these are all my points. If you are not comfortable with this approach, please feel free to ignore all this advice. So if whatever the approach you feel comfortable, please do follow that. Okay, and one more takeaway here is that when you look at the gradient formula, you just think of what are all the variables that affects my final gradients. Okay, so I am computing the gradient of this weight with respect to the loss with respect to this weight. So what are all the variables that directly affects the value of this gradient, or in other words, so let's say I want this gradient to be 0, or under which condition the gradient can be 0. Okay, so there are many possibilities. So no matter what these values are, if my input becomes 0, then my gradient becomes 0. This weight will not get updated. Okay, so my input, or in other words, in general, input to the neuron, here we denote it by x, but in general it could be an input from the previous layer. Okay, so if any of the input from the previous layer is 0, then the gradient for that particular weight will not get so it becomes 0, so the particular weight will not get updated. That is one takeaway. Even suppose if xi is not 0, okay, then what could affect my gradient values? One thing is this f of xi can become 0, or 1 minus f of xi can become 0, or if my f of xi in this case becomes 1, then this term becomes 0. So all possibilities are there, right? So we have sigmoid. So I'm just trying to correlate the content across the weeks, so that if you understand everything with this simple example, then when you study those contents, you can correlate them. Okay. So we have some saturated activation function. Saturation in the sense it is possible that this function can take values 0 and 1. So I am using a derivative of that function, which is f of xi 1 minus f of xi. So it is possible that we are just saying it is possible that these values can become 0. Okay, so therefore it is possible that my weights or the gradient for a particular weight can be 0. Okay, so these are all the some, whenever you encounter these formulas, you try to think about in this perspective as well. When this or like this, when my gradient becomes infinite, is it possible? Okay, 0, now we explored it. Can it become infinite, or is there any, which means can it explode? Okay, so things like that. And of course, if you have more than one data points, you can simply sum across, some compute the gradient by summing across the all samples. And same thing goes here. But one interesting observation is that my weights are influenced by the inputs. Okay, the gradient of the weight is influenced by the input values, but bias is free. Okay, it is not it won't get affected by the input value. Even my input becomes 0, it is still possible that during the next iteration my bias value gets updated if these quantities are not 0. Okay, and we term these together as a parameter. Both are learnable parameter, but one parameter like weights is influenced by both the activation function as well as the input values, whereas bias is not influenced by the input values. Okay, so when I say input, it is input received by the neurons from the previous layer. Okay, and you know that, say for example, the output from this neuron becomes 0, then it is shared by, okay, this 0 is shared to all other neurons, but there may be another neuron that contributes. Okay, if it is 1, it is also connected with all other neurons. So in this case, even though one of the neuron becomes 0, other neurons are giving some values. What I'm actually doing is, before the activation function, I am summing all these up. That I need to remember. Okay, I'm summing all these up. So my when I update the weight, it is possible that gradient cannot be 0. Okay, so yeah, these are all some important takeaways that I would like to share here. Yeah, followed by, we discussed about approximating some nonlinear function or any nonlinear function using network of sigmoid functions. Okay, so we just visually demonstrated how it is possible to approximate any given function using a single hidden layer with kind of infinite neurons. Okay, I'm not going to talk about that. That is quite straightforward. It is all about if I have two sigmoids. Okay, I'm just essentially, for different values of W and B, I can shift this sigmoid left or right. Okay, for this sigmoid, I can kind of shift it further. So I can put another neuron here, which simply add this and then generate some tower. Okay, and we have these applets in the lecture slide, so you can interact with it, how these sigmoids are actually shifting as we change the values of W and B. Okay, so of course W won't do shifting. Increasing W and B, increasing the values of W changes the slope or steepness of the sigmoid. Changing the values of B actually shifts the sigmoid. Okay, and please do play with those applets and try to understand how this shifting are actually happening. Okay, I hope everything is fine so far. So if you have any doubts, sorry Himansh, So you said we can't hear you for that 680. Okay, shall I move on to the next slide?
Yes, sir.
Yes, sir.
Okay. And one thing is that even if you, after this revision session, please go and solve all these graded and practice assignment and quiz questions and try to understand the process. Okay. Yeah. So finally, the very important week of this entire deep learning is this artificial neural network or fully connected or feed forward neural network, different names. Okay, so we call this as feed forward neural networks, and also they are fully connected. Okay, and we know the reason why it is called fully connected, because we have something different called convolution and recurrent neural networks. So we just call this as fully connected. And most often, I hope you don't have any difficulty in understanding the forward propagation of this neural network. That is quite straightforward. It's simply matrix vector multiplication up to the end. It's not a big deal. It's very easy to follow. But the only difficulty that you might face is that understanding the backpropagation algorithm. Backpropagation, in fact, is if you ignore all those derivations, okay, understanding the derivation is extremely important when you kind of come up with your own modules and write backprop for that module. But from the exam point of view, you need not to remember all those steps. Okay, we may give you some intermediate result and ask you to compute the gradients or ask you to derive the gradients for that particular kind of module. Okay, but understanding the backpropagation algorithm is really important. As I mentioned earlier, for a single neuron, the backpropagation also starts by computing gradients at the output layer first. Okay, so it has to compute the gradient at the output layer with respect to the gradient of loss with respect to the output from output layer. Okay, so that we denote it by y hat. So of course, this formula is true for softmax function, where we assume we use softmax function at the output layer. You have to be really, really be careful which activation function we actually use at the output layer. So if it is softmax, you can use this formula. If it is kind of sigmoid, of course, and also the loss is cross entropy, it is not mean square error loss. So if it is mean square error loss, then you have to change the formula accordingly. Here we assume this is we use softmax and also cross entropy. The first step is always to compute the gradient, and then we have to pass this gradient to the previous layers. Okay, so that's where this entire iteration process starts. So we start from the output layer and then we pass the gradient to the next layer. And again, I hope this this diagram might be helpful. So it's like I'm using softmax here. Okay. Okay, so there are different way of using softmax. Let's say I have some nonlinear values, of course, this linear component, and then I'm using softmax here. But when I say softmax, in fact, all these neurons are connected when I say softmax, right? Because to compute softmax, we take this e power for a particular neuron. Say if it is a single first neuron, then I take e power a1, a31, but I'm just writing it as a1. And then we divide the values by all the neurons a1, and then a2, a3, a4, all these four values. Okay, so this is somehow connected. So the important thing is that we know I have a gradient entering here. Now I have to pass this gradient across this softmax layer. So the formula that we actually saw, gradient of AL, it is actually for the last layer. Okay, is minus EY of minus y hat. So it's very straightforward. Y hat I already predicted. I have a vector for y hat. y is an true label and E is one hot encoding. Okay, so I use this one hot encoding of the true label and then I simply subtract this. Now I get again a vector. So that is what I have. So that is what being transmitted to all my previous layers. Okay, so maybe at the first attempt it seems kind of very complex to understand, but it is not complex in if you are, once you understand it, you see there is nothing in it. Okay, but some effort has to be put in order to understand entire backpropagation algorithm. You solve the graded assignment questions, and if you have trouble understanding the backpropagation algorithm, please put it in the discourse, or if you really want to understand it very quickly, if you don't have enough time, ping me in the WhatsApp group. I try to join. Okay, so once we compute this gradient with respect to the output layer, then we enter into this recursive process. This is really simple. To compute a particular weight, so you just think of this as what are these quantities, whether it's a vector, scalar, all these things. AK is a vector, right? And HK minus 1 is the actually output from the previous layer. Let's say I have 3 neurons in the output layer and 3 neurons in the previous hidden layer. Okay, so I have gradient of L, okay, AL actually, which is a vector, and then I have HL minus 1. Okay, here we are using K, but I'm just, okay, or let's use K minus 1. So this is a vector. Now what I'm doing is I'm simply, this is a transpose. Okay, so since it is 3 by 1, taking transpose is 1 by 3, and this is again 3 by 1, and then if you take an outer product, then it becomes 3 by 3. You simply subtract that with the weight values. Okay, so it's a, as you know, so forward prop is simply matrix vector multiplication. You have a matrix vector multiply, matrix vector multiply. It keeps recursively follows this step. Back propagation is also same. We have a vector, we pass it through some nonlinear function, and then we also have a vector, and then we take an outer product. Okay, instead of matrix vector product, we have an outer product, and then we compute the gradient for the entire weights of that particular layer using this outer product, and then we update it. Okay, and also note the similarity. Here my gradient is function of the outputs from the previous layer. Okay, HK minus 1. So it is function of outputs from the previous layer, whereas the bias is not function of the output from the previous layer, so it won't get affected. Okay, so the same steps follows. So that's why I'm keep insisting, try to figure out the patterns and connect the dots. Okay, so once again, okay, so I am going to repeat this process recursively. So now I have dou AL here. Somehow I computed the weight updates. Now I need dou L minus 1, right? Then only I can compute the weight updates for the previous layer. Okay, so what you have to do, we have this non-linearity here. So we have to pass all these gradients through this non-linearity, and this is going to be element wise multiply. I have two vectors. Previously I computed the outer product. Now I'm going to compute the Hadamard, the element wise product. Okay, have elements. So if we, okay, let me display the formula, then I just move on. Of course, I have this dou AL, and then I update the weights. Then I have this HK minus 1. So I have to compute this dou HK minus 1. It is simply, once again, it is a matrix vector product. Then I have to pass this dou HK minus 1 through this nonlinear activation function. Okay, so again, we have a single sigmoid. The neuron receives an input. Then we have to pass this through this derivative of this activation function. then it reaches this linear part. Okay, so that's what we are doing here. This is also a vector, and it is an element wise. You compute the activation functions element wise. So you have a vector, and then this symbol actually denotes an element wise product. Okay, so once you have this, you compute all these steps, then everything else is repeated recursively. Okay, so I'm not sure. So by the way, let me take a poll. How many of you are comfortable with backprop in fully connected layer? The chat box, you can enter it in the chat box.
Sir, can you please solve a simple little example?
No, that example
That
is
is,
there in the graded assignment, right?
yes, yes.
No, I mean, yes, I'm insisting you to solve that. So that's why we actually came up with a numerical example for the graded assignment. Okay,
So there was also a question in a quiz too.
not in quiz one also we had this question, computing.
Sir, in quiz too there was also a question from backpropagation, I think.
Yeah, that is for convolutional neural network, right?
No, sir,
Yes,
just
sir.
one
Of course.
one neuron in every layer.
Sorry, are you talking?
Yeah, so in quiz 2, there was a question with backpropagation, one neuron in every layer, and there were like 3 layers or something.
Yeah. So yes. So of course, in quiz 2 we focused on this convolution part. Okay, so and also how, that's why I'm saying, I mean, you should know how to compute the back propagation for different functions. So in the workshop, or even if you take any Python, sorry, not Python, any deep learning frameworks, okay. Of course, this is not related to exam, but I think this is the right time to talk about that. They actually implement backprop for every operation. Okay, so here we encounter some operations like if I have matrix vector multiplication in the forward prop, then what should I do in the back prop? If I have some nonlinear activation function in the forward prop, then how do I compute the activation for the back prop? So like that, in deep learning frameworks, they implement this back prop for each operation, even including when I add two inputs during the forward prop, then what happens during the same operation during back prop. Okay, so that skill is extremely important. Okay, of course, in quiz 2 we gave you one operation, that is max operation. That's where all the difference comes in. Okay, so I compute for during the forward propagation, taking the maximum value is a straightforward process, nothing difficult in that. But during back prop, what really happens? Okay, so that you should be in a position to do that. We may come up with a different function. So instead of max pool, of course, the straight is min, or we may ask you to take average pool. Okay, of course, don't worry about this end term exam, but uh, who are going to watch this in the next term. Okay, so I'm kind of telling to them. Okay, we come up with different activation functions and different sort of these reduction functions, but we expect you to be all these things involves taking derivative. So you for this end term exam, you need not to bother about all these things because we are covering so vast content. So due to time constraint, we can't actually take some complex questions. So I hope you feel comfortable with the end term exam. Uh, Given that you have very short span of time, you don't need to bother too much about this back prop to con layers. Okay, and once again, I'm keep re-insisting. Ensure that you are able to solve all the graded assignment and practice assignment questions. Ensure that you are able to solve quiz 1 and quiz 2 questions. Okay, even if you are not able to solve this back prop part, that is fine. Okay, of course, from the exam. I'm just telling from the exam perspective, but you should have good grasp on all other concepts. Yeah, so once you come to realize that, so after putting so much effort and once you understand the backprop, then I mean, that is really a good thing. Please try to do that, but do that after the examination, not now. Okay. Okay, so should I repeat this backprop part once again? Or
I
That's
have
fine.
2, 3 questions. Okay, for that, the way we are doing the manual calculation. So
yeah,
generally, what we are doing, if we come to the last layer, for example, that AL layer. Okay. So generally,
okay.
what we are doing, we are getting the A3. For example, I have a 3 hidden layer. So we just take the simple softmax and we get the S3, which is equals to my Y hat, right? Up to
Yeah,
that, no problem. Now,
yeah,
when we are going to calculate the loss function, okay.
yes.
So what we are doing, we are taking the current Y and we are multiplying with this log of 2 or whatever you are giving with the Y hat or H3. And that
Yes.
is going to my loss function. If I have multiple value, we are going to sum it. Okay. Now, when
If we use cross entropy, right? Okay.
yeah, I'm talking about the cross entropy, the example you given. So it is
Okay.
nothing but
Let
Y
me put
into
let me put some numerical number. Let's say you compute L is equal to 0.5.
0.5. Now, when I'm going to calculate the gradient, that AL, grad AL of L theta, this EY is there. Okay. Suppose I have a single value, then what I will do, I will take that particular, for example, 001. And for example, suppose Y hat, I got some value. Okay.
Okay.
So we are just minusing it, right? That means simply we are putting as an Y minus Y hat for a single value. But if in exam, if we given the 2 value, means it's a metric, then how we are going to minus this AL?
Sorry, I don't understand what do you mean by single value. So can you repeat that? So now, okay, let me draw it here. So let's say I have 3 neurons, and after softmax, I have a vector y hat vector, which is the probability for each class.
Mhm.
Then what you're saying?
Yeah, so for take some example like 0.1, 0.2, 0.3 for in Y hat, I have 3 value, for example.
Okay, 0.1,
It's
0.4,
and
0.5.
0.5. Okay. Now suppose my Y, the true value is given, suppose 0, 1, 1, 0, 1, 0, 0, 1, 0. Okay.
Okay.
Simply to getting a gradient of YL in the last layer, output layer, is simply minus it, Y minus Y hat, and we will just take the negative of that. That the formula is telling, correct?
Yeah, that's correct.
Now suppose instead of giving 0, 1, 0, I have one more value here. Means we have given 2 output and my Y hat is also coming 2. Means multiple, I'm telling about the multiple value. Then the same way it is going to subtract.
So you mean multi-label classification?
Yes, multi-level. That is not going to come in the question, right? For the manual calculation, correct?
Yeah, yeah. So it could be anything. The output vector, I mean, whatever your why you can directly use them. That doesn't matter. I mean, if it is a multi-label classification, of course, when we go for multi-label classification, we don't use softmax because it doesn't make sense. Because softmax gives the highest probability for one class, then we can't, say for example, this is so I say it's a 3 class, so it's the softmax says the prediction is class 3. But if it is a multi-label classification, you can't simply take the next value as the one other class. I mean, say if it is an image classification problem, right? Let's say I
Right.
have banana and then I'm sorry, maybe some orange, okay? And then if I use softmax, it says with high confidence 0.9, it is banana, okay? And then it says it is 0.1, it is orange. But I don't want this low confidence code for another class because I know that with high confidence, orange is also there, right?
Right.
In the true label, it says orange is also there. So you can't use softmax in the multi-label settings. In multi-label settings, we in fact go with sigmoid for each class. We replace, I mean, the output layer contains the sigmoid. Now it makes sense. If I use sigmoid, then my probability is constrained only within this class, right? Either it is banana or not, it is orange or not. Do you understand?
Yeah, I understood. I got your point. Okay, now I got this output layer. Okay, now I'm going into the loop and I'm doing this gradient calculation for the weights. Okay.
Okay.
So simply, for example, suppose I have three done layer, A1, A2, A3. A3 I have already calculated. I have the A3 now. Okay, means grade of A3. Grade of A3 I have already have. Now I'm going to calculate for the grade of A2. So what I will take the weight of W3 and I'm going to take A3 and then I'm going to sigmoid of A2 and 1 minus sigmoid of A2 for getting this.
Gradient of A2.
Yeah, I'm talking about the last one. The input gradient with respect to layer for pre-activation functions.
Yeah, that's correct. What you are saying is correct. So you take AK and multiply that with the weight of that particular layer, say W3 transpose. Then you will get again a vector, right?
Right.
And that vector, of course, this vector is nothing but an output from the previous layer, right?
Right.
So it is HK minus 1. Then you are computing. So you have gradient of HK minus 1. Now you have to push this gradients to the next layer. That only gate is this nonlinear activation function. So which means it's element wise product, because during the forward prop we did element wise product. Sorry, element wise computation. So we have this vector, and then we already have these values, right? So during the forward prop, I already computed G, not G, say for example, f of x. Okay. During back prop, I need to compute 1 minus for sigmoid I'm talking about. Okay.
Yes,
so
yes.
it's 1 minus f of x. I should have this value x stored somewhere. Of course, when implementation perspective, it's fine. But what you're saying is exactly right. So you have this vector, and then you have another vector, okay, which you compute using the derivative of the activation function. We have two vectors now. We compute the element wise product between these vectors. So the output is also a vector.
Okay, but now here we have not given any formula for the bias. We are creating the gradient of it. Okay, so here there is no role of bias internally for when we are calculating for in the layers like A1 or A2.
No, bias has no role to play during. It doesn't influence. Because bias is not connected to or not influenced by output from these neurons, right? So I have Wx plus B. Only my weights are influenced by this X, not the bias, right? So again, during back propagation, bias has no role to play. It can't influence the gradients in the previous layer.
So bias will come only when we are going to calculate the last one, that with respect to its parameter, means the first layer, I think, the A1 side. And then during the back propagation, when we are going to update the weight, that time only we need to consider the bias. And again, we need to apply in the formula that Wx plus B, and the B is going to take the new A1, A2, A3, and then the same weight is going to interloop, correct?
No, I'm not sure whether I exactly got you. Again, I think it's better to go with some. Okay, can you talk with respect to these diagrams, previous diagram?
Yeah, you just go to diagram. The diagram is 3 layers. Okay. Yes. Okay, so now I got the A3, I got the grade A3, I got grade A2, I got grade A1. Up to that.
Okay.
Now here in A1, I need to update this weights, right? Once I reach to the first one, correct? So I need to update the weight, and I need to update the bias also, correct?
Yeah, of course, you need to.
So when we are going to update the bias, so I have the grade A1. How I will get the I updated the weight. I have updated the weight. How to update the bias then? Here?
It is equal to grade A1.
Oh, it is simply just a grade 1.
Yeah.
Okay.
Answer weight part.
Weight is you have this
grade W.
That grade A1, that is the grade A1.
Yeah, the weight is grade A1 times H0 transpose.
Yeah.
And what is H0 X?
Yeah, in this case it is X.
Okay.
B is simply my grade A. So now I got the grade W and grade B. Now I will apply the weight update formula, and whatever the weight we are going to get, then again we are going to use the same feed forward to update to get the loss function. If the question is that after one iteration, what is going to be the loss, the way we are going to calculate, correct?
Yeah. So which means we use this word, okay, update the weights or after one iteration. So for of course, you have to be really careful with these words. Okay, so we use either iteration or epoch. Okay, and by the way, since it is manual calculation, most often we stick with SGD. Okay, so where iteration and epoch both means the same. Of course, from exam perspective, most often it is like update the weight means we give you only one sample, right? One data point, especially when neural network on CNN or RNN. We give you one data point and we expect you to compute the loss. And after one iteration means you backprop and update the weights. So that is what we mean by one iteration. Okay, in single iteration we update the weights. So which means we subtract the gradient. Of course, we have to look whether we have mentioned the eta value. And then compute the loss means with the updated weights, you compute the loss once again and see whether it decrease or increase.
So for weight one, you told that grade A1, H0 or X transpose. For W2, we have to take grade A2, H1 and transpose, right? When we are going to calculate
Yeah.
it. And then again, we have to minus it from W equals to W minus theta W1, which is nothing but grade A2, H1 transpose, correct?
Yeah, that's correct.
Okay. Okay, understood. Thank you. My side. Others can ask.
Yeah. Please, I am waiting for us because this is really, I mean, even if you don't understand for CNN, RNN, I really want you to understand this. And then when you get a free time after this course, then you focus on CNN and RNN.
I didn't understand the last part.
Sorry, which part?
So, so for example, you give one neuron in every layer, and can you just take an example of one neuron in every layer, 3 layers, and show how exactly it works?
Yeah, that is quite easy, but one neuron, of course, I do that now, but one neuron reduces everything to scalar, right? So when we have vector, things is a bit different, but the process remains same. Say, for example, if you really want, I have, let's say, 3 neurons, okay? So I have an input, let's say X, then it produces an output H1, and then I have intermediate value A1, which is equal to X. And then A2, of course, I have W here, W1, let's say. Then H2, and then W2 here. And then A3. And finally, I have Y hat. Okay. So I have, I mean, we have this true label. And let's say I'm asking you to compute mean square error loss. So in mean square error loss, you can, my gradient of loss with respect to Y hat is simply Y hat minus Y. Is based on whether it's Y hat minus Y or Y minus Y hat is depending on the formula. Here I'm assuming it's Y hat minus Y whole square. Okay. Now I must have given you these values of Y, and then you should have calculated this Y hat. Now I have some number. Let's say the number turns out to be 0.5. Okay. Then what should I do is I have this 0.5. Then let's say again, for the sake of this example, I can consider sigmoid neuron. So I have this sigmoid neuron in all these 3 are sigmoid neuron. So what should I do? I have 0.5 here. Then I have to move this 0.5 to the next layer, right? So to do that, I have this nonlinear activation here. First, I have to pass this value through this nonlinear activation function. Since it is sigmoid, I have this sigma of A3. So this is the derivative of this sigmoid. Okay, remember that I am computing this derivative or computing these values with respect to A3, whichever I got during the forward propagation. Okay, so I have these values, plug in A3 value and solve this, you will get another number. Let's say I get number as, since it is sigmoid, it cannot be greater than 1, say it's 0.3. Okay, so what I do is I simply multiply this 0.5 and 0.3, so I will get some value. What is that? 0.5 into 0.3. Okay, so now okay, let me display the formula. Maybe I try to relate this, even though now it is with respect to scalar, the same thing is happening. So now we are doing something like this. Okay, so I compute this belongs to this. Okay, I'm computing gradient with respect to the activation function. Here I'm getting a scalar. In general, I will get a vector, and then I multiply these gradients with the dou h k minus 1, which means here whatever the input to the neuron from the back propagation perspective, my input is y hat. So now you can think of this as y hat. Okay, I'm simply directly multiplying y hat with this sigma a3 1 minus whatever the derivative of the activation function. Now I get a number. Okay, so what should I do next? I have to update the weights. Okay, okay, how do I delete? Okay, now let me. So we have computed some quantities 0.5, and the derivative of this is going to be 0.3. So I'm just writing it down here. I have 0.5 and then 0.3 here. Okay, so I have to, in fact, the scalar, the entire process is scalar. Here next I have to update the weights. Okay, so I might have chosen some weight here. Let's say in W3 is equal to 1. Okay, this is my weight, so I need to update this weight. Okay, so this weight depends on hk minus 1 transpose. So we store that value into h2. So let's say h2 is also, say, let's say minus 1. Sigma, it's not possible. So let's say plus 1. Okay, it says my internet connection is unstable. Are you able to hear my voice and this screen clearly?
Yes, yes.
No
Yes, sir.
problem. Okay.
Yeah, no problem.
Okay. Okay. So now you just focus on these values. Okay. In the back prop, what we have is I have this H2 which I computed during the forward prop, and also weight given to me. And during the back prop, what are all the values I need? I need some values. 0.5 is here, 0.3 is we computed during back prop. So how do we connect all of them together? Okay, so we have this value now, which we substituted it as plus 1. Okay, so what is this dou ak? That is what we computed here, 0.5 into 0.3. Okay, so yeah, it turns out to be a simple scalar multiplication for this example. But if you have a network, then it is going to be an outer product. Okay, so this is simply going to be my gradient of W3 is simply my H2, okay, which is the value of 1. So it is H2 times the gradient from this neuron. Okay, so I have this A3 here. So dou A3. So dou A3 is simply going to be 0.3 times into 0.5. Okay, of course, 5 into 3. What is that? 15?
0.15. 0.15. Yeah.
Okay, 0.15 times H2 is 1. So it is 0.15. Okay, so this exact process keeps repeated for all the neurons. Okay, now in this neuron 0.5 is the input. For this neuron, what will be the input? Mukesh, you can tell. Okay, so here we have W, then I update this W, by the way. Okay, now I computed the gradient, and we have to use W3 minus eta times the W3. Oftentimes we set eta is equal to 1 if it is not at all important. But be careful whether we have mentioned some other values for eta. Now I updated the W. Okay, now what should I do? I have to compute dou H2, right?
Right.
So to compute dou H2, so again in this example, since it is a scalar, again it's a direct multiplication. Okay, so 1 into
0.85.
0.15. Okay.
85. 0.85.
0.85. Why? Why is that the case?
The new W.
Okay, that is updated W. That's fine. You after subtracting it, new W is going to be 0.85. So for the next neuron, you are going to repeat this process, right? So what will be the input to the next neuron? So here the input, so I am talking from the backprop perspective. So I am calling this as an input and this as an output. Now we are talking backpropagation. So here the input is 0.5, which is coming from computing the derivative of loss with respect to the output layer. So what should be the input to this neuron? How do you compute that?
0.15. So A3 was the input to that.
Yeah, so in this case it's 0.15 because it is scalar value, but we have to use this formula. Okay, so if we have a vector, again we multiply. Remember, this is transpose now. Here we are directly multiplying W because we have only single value. But if I have a network, then I have to take a transpose. Okay, that is also makes sense why we intuitively make sense why we need to take transpose. But that's one important step you have to remember. But by the way, for manual calculation, we don't really ask you to compute so many things. Either we give you a simple matrix, even transposing the mat. If our intention is you to focus on whether you understand this concept, then the matrix might be symmetric matrix. Okay, but this is important. We are computing the input to the next layer by multiplying the gradient from the previous layer with the transposed weight of that layer.
But sir, we are not going to update the weight during the backpropagation, right? So W3 cannot be 0.85 when we are going from W3 to W2, right?
Yeah, that makes sense, of course. I mean, in general, what happens is backpropagation means we compute the gradients, then we update unless if I don't do any forward propagation, right? If it is a stochastic gradient descent, then updating at the point makes sense. Because anyhow, I'm going to fade in. Sorry, Mukesh.
Your voice was breaking.
I don't know why my net connection. Is it fine now?
Yeah, fine.
Okay, so of course, in general, we should not update if we use batch gradient descent. Okay, but if we use stochastic gradient descent, then updating is not going to affect us.
Right. Agree. Yes. Okay, understood. Yeah.
Okay.
What we will do in the examination, it will be given that it is SGD.
Yeah, we either mention SGD or we ask you to compute for one iteration. Oftentimes it is going to be one sample, right? So we given that you don't have time beyond 90 minutes, you don't want you sit for more than 5 minutes on a single question. But in general, you have to focus on this word, whether we mention it is a stochastic gradient descent or batch gradient descent. Okay, so as far as I remember, I didn't mention, I only focused on SGD. Okay, please, of course, even if you don't get all of this at this moment, please sit and think about that. Okay, so you have 2 more days, right? Friday, Saturday. Okay, so if you are not able to understand all of this, even after spending 2 to 3 hours of time, okay, please ignore it, move on to the next topics. After the exam, you can sit and think about that. Okay, because your final grade won't get affected because of these questions. But if you really want to get good grade, then understanding this is really important. Okay. Okay, shall we move on to the next, or
Yes, sir.
Yes, sir.
if anyone has doubt on this backprop, of course you must have doubt. Please, okay, in final word, you solve the graded assignment and quiz, and if you have doubt, post it in the group or in the discourse. I try to answer it. Okay. Of course, if you take a numerical example, that will help you. Don't play with equations. It may not make sense. So take that numerical example, try to calculate those values, see whether you get the similar or the same value. If not, if you get if you get stuck at some point, please don't hesitate to put it in the group or in the discourse. Yeah, so after this week, so once if you understand this backprop part, then everything falls in its place. You don't need to put a lot of effort to understand the rest. Because in the subsequent weeks, we discussed about different types of gradient descent algorithms, and especially NAG, momentum based gradient descent. And then we also different way of doing this weight updation, either using stochastic, single samples, or batch gradient or mini batch gradient. And we also discussed about different types of learning rate schedulers, and most often you don't need to remember these formulas. If required, we mention the formulas. Okay, we know that it's too hard to remember all the formulas in this entire course, so wherever appropriate we mention the formulas. Okay, if it is really simple formulas, you try to remember them. You write down in the notes and try to remember them. Yeah, so we discussed about all these different types of searching as well, line search, all this. And of course, solving again graded assignment questions will help you to understand all these concepts, especially both. You try to solve both practice as well as graded assignment. If there are programming questions, you don't really need to bother about them, implementation aspect, but try to understand the code in the lecture notes at least. Okay, what's going on in the code, try to get it. Yeah, so then in the subsequent weeks, we discussed about these adaptive gradients, which I already discussed in the previous revision session. I just go over it quickly. Now we know that in a single neuron case, we discussed about computing this weight, which is somehow directly get affected by the input to the neuron. Okay, so if I have a network of neurons, if so many inputs are 0, then it is very obvious that weights in my first layer, okay, will get affected. Okay, so many affected in the sense they won't get updated. If there is a single feature that always gets a value and all the rest of the features are not getting the values, then we know a particular weight gets affected very often than the other weights. So this creates problem in terms of convergence. Okay, whether you use adaptive gradient based optimization algorithm or a simple plain gradient descent algorithms. Okay, convergence is kind of, it converges. Okay, but how fast it converges is the question. So when we really have billions of parameters, we don't have time to train the algorithms for months or years. So we really want a good optimization algorithm. And in this point, I would say, for a single training, if you think about tech giants like Google, Facebook, those who are training really big model, if you come up with the algorithm, okay, an optimization algorithm that saves, say for example, it converges 10 steps ahead compared to the rest of the algorithms, then they save millions of dollars. Okay, so there are a separate research on it, trying to come up with a better convergence algorithm, even with the help of second order gradients. Okay, so that's why optimization is the core part of deep learning. So to really understand any optimization algorithm, you should really have a good understanding about the computation of gradients for any network. Okay, not just for fully connected. You can think of all the networks are actually composed of unique layers. Here we call it as fully connected, and then in convolution we have convolution layer, like that. Okay, so once you understand them, then we can use any advanced optimization algorithm on it, and you will really able to understand them. Okay, yeah. So adaptive gradients are in fact based on tracking the gradients. Okay, it's kind of bookkeeping of the past gradient values and make use of them to understand the loss surface, how the loss surface is, then make a decision accordingly. And remember that whether we use an adaptive learning scheduler or adaptive gradients, we are in fact somehow computing this learning rate. Okay, so this learning rate is adaptive based on the previous gradient values. We can set the learning rate scheduler manually. We don't call that as adaptive. Okay, it's simply function of iteration. Here we use the word effective learning rate, but of course trying to merge them into a single terminology is quite difficult. But just to distinguish it from the previous types, we call this as an effective learning rate. Okay, yeah, so we have so many different varieties of adaptive gradient based algorithms. Like most important one is Adam, and then Adam, and we have ADAMAX. All these steps starting from the basic grad, we look into the drawbacks of each types, and then we eliminate the drawbacks and come up with a new algorithm. Okay, and Adam is the most important one. Of course, AdaGrad simply stores the previous history. Okay, and remember, we are squaring the gradients. Squaring is really important. And then we discuss what's the problem with this approach. Come up with Adam, and of course, you don't need to remember all these formulas, but understanding is important. Okay, so we use bias correction here. So having a good idea about what we mean by bias correction and why it is required, all these things are important. Okay, if required, we give you the entire formula. In quiz 2, we have given you the entire formula. Asked you to compute something from those formulas, right? Like that, we give you the formulas wherever appropriate. So I think week 4, 5 focused on these concepts, especially different types of optimization algorithms. And then we discussed about this regularization techniques. Of course, if you are able to solve quiz 2 questions in regularization techniques and also graded assignments, that is more than enough. And of course, we already discussed all these things in the previous revision session. Please do watch them. So I quickly move on to the next one. Okay. And by the way, do you have any questions in these weeks? Week 4, 5, 6, 7, 8. Because you recently.
Yes, sir. I have 2 questions in week 6.
Week 6. What is that content? Yeah. Please go ahead and ask the questions.
Right. So, in the formula, when we are trying to find out the effect of eigenvectors, there is 2. Let's say in EVD there is Q and Q transpose, right?
So you are asking about in the regularization techniques, right?
I'm asking in the bias and variance.
Bias and variance. Okay. Do I have it on this slide or? So yeah. Okay, Himanshu, please proceed. I try to understand it, or I move on to this slide.
Okay, so you don't have it here. Remember when we tried to find out lambda upon lambda plus the alpha?
Yeah. So yes.
So
I think that
before
is
that,
with respect to L2 regularization, right?
we generally try to find out the effect of regularization, where we conclude that regularization will, let's say, it will minimize the direction in which the eigenvector is less, and then it will try to maximize the direction in which eigenvector Like,
Yeah. So
as
that
in,
is actually with respect to L2 regularization. Yes.
so in that we have two metrics, like when we perform EVD on that diagonal, on that like middle term, which are Q and Q transpose.
Okay.
So what we say is first Q transpose transforms it, and then we use that diagonal matrix to scale it, and then Q again transforms it back.
Yes, that's right.
Yeah. So like since we are I want to ask what effect does scaling it in a transform landscape versus scaling it in the original landscape makes. Because see, if we are transforming it, if we're scaling in a transform landscape and then we are scaling it back, like does it have any extra effect that if we skip the whole transformation, it will like not have that effect?
Yeah. So it is like transformation in the sense. So we have some matrix A, then we decompose that matrix into U sigma V, and then we do the interpretation is that you multiply a vector X here, then it does transforms and then scales it and then rotate it back, and then you get. So instead of doing all these steps, why don't we do with this A itself, right? That's what your question.
Like why don't we just scale the A instead of like transforming it and then transforming it back?
No. We are, in fact, what we do in that lecture is, so we have this Taylor series expansion, right?
Right.
First, we start with this Taylor series expansion. So we have the gradient, and also we have this Hessian. Okay.
Okay.
Okay, we have these terms, right? So we have this constant term and then first order derivative and then the second order derivative. Okay. So we kind of try to explore what happens if I somehow incorporate this Hessian into this, this weight update rule. Okay. So we try to study the effect of this Hessian. Okay. So while studying that effect, we decompose this Hessian matrix. Okay. And then that's where we talk about all these rotations and then scaling and then rotate it back. Okay. We are actually studying the effect of Hessian matrix. Of course, you can directly do that with H, but in just to get some insights, we need to decompose and then trying to see what it really does to the vectors. And your question is, why don't we scale it somehow in a original space? Okay, so but how do you say, for example, in this diagram, this W star. Okay, so this is before applying regularization. Let's say I have W1 star, W2 star. Okay, so this is my W1 and this is my W2. So we have no idea whether how much we need to change this W1 and W2, right? So scaling means we are doing in the same space. So somehow we have to figure out the value of alpha and beta for this W1 and W2. And how do you find these values for alpha and beta? What is the mechanism if you really want to scale this? Of course, when I say scaling, it is not scaling up. So all the weights are getting shrinked. Okay, it's not blowed. I mean, it's not get scaled up. It's scaled down. Okay. So how do you determine this alpha and beta? That will be a trouble, right? Because in this diagram you can see that which one is more sensitive, W1 or W2? Can you figure out that with the help of this loss landscape?
W2.
Yeah. So if I change W2 a bit, then my loss will change drastically. If I change W1, then loss won't change much. Okay. So coming up with, manually coming up, not manually, we need some kind of approach to scale this W such that it won't affect my loss altogether. right?
Right.
So that's where actually this Hessian comes into picture, and of course this is completely why we decompose using SVD decomposition is just to get some insights. Okay.
Okay. Okay. Also, sir, can you open lecture 7 of week 6?
Lecture 7 of week 6. What is that? Can you tell me the content of that one? I don't know.
Injecting Gaussian noise at input.
Injecting. So are you able to see that?
Yes.
I don't know. Can you tell me the slide number?
It's different slide. Okay, sir. Can you just go back?
Noise to the outputs. This is a noise to the input.
Noise to the input.
Yeah.
Yeah. So can you go forward? Where we at the value of epsilon square. So go forward.
Next.
Yeah. So here. No. Yes.
So I think it takes some. Let's check. Oh, sorry.
Right. Since we originally envisioned epsilon as of variance sigma square,
Yes.
just below the but in the second last step on right hand side, we are using epsilon square, right? Since they are independent.
This one.
Yeah. So since they are independent, we will have some multiplication of those, right?
Okay, let me go through the previous steps. Then only I get the idea.
Okay.
Give me a second. This is a model. Rearrange. Right. Expectation. Okay, so can you ask this question now? What's your question, Himanshu?
Yeah. So in the second last step,
This
for
one,
this
we're
second
talking
term,
about this step, right?
yeah, this step last term, what we
Okay.
will say is since Wi and EI are independent of each other, we will write as expectation of EI into expectation of sum of WI, right?
Yeah.
And then since here EI is square.
Epsilon you are talking about, right?
Yeah, epsilon is square.
Yeah.
And in the at the beginning we told epsilon variance of epsilon is a sigma square. So variance of epsilon square will be same because at the end we have substituted sigma square.
Yeah, that's correct.
So why will squaring and distribution will have same variance?
Expectation of, okay, I will look into that, Himanshu. I work out because I don't see that clearly here. So I work it out and come back to you.
Okay.
So you are asking how
also,
do you
sir,
go from this step to this step, right?
Yeah. So what we did is we used expectation of epsilon square, and since we defined epsilon square has an sigma square variance, we just wrote sigma square. But shouldn't it be sigma square of sigma square?
Yeah, I will check that.
Okay. Fine, sir. You can move on.
Okay. Where we left off. So yeah. So of course. So after regularization, we kind of dig deep into different activation functions. So once I think activation functions is not that much difficult to, once you've understand how the gradient works, and once you know what is the derivative of the activation function, of course, for the simple activation functions like it's going to be either sigmoid or tan h or relu. Okay, remember the derivation of all these derivative of all these activation functions, because we go for different activation functions because they have problem. While computing gradients, we encounter some problems like vanishing gradient and exploding gradient. Of course, if it is a saturated neuron, then we don't encounter this exploding gradient. But all these activation function concepts are related, connected to computing the gradients. So know how to compute the gradients for different activation functions. Of course, when we give some examples in the exam, we give you kind of network like this, and we expect you to understand how backprop works for this thin network. So that is more than enough. Okay. And yeah, so ConNet. So as far as ConNet is concerned, so you should be good at
Sir.
Yeah, please.
Before proceeding to ConNet, I had one doubt in programming assignment 6, question number 3.
Okay.
So, like, if you have access to those, then it's okay. Otherwise, I can just say what the question is.
No, I have it here. Don't.
Okay.
Assignment 6, right?
Practice assignment. Yep. Question number 3.
Okay. This one.
Right. Yeah. So we know that we can compute the value at 0, 0, which is the minimum value -1. But how to proceed for this question in exam?
Sorry, which question? Sorry,
question number 3.
No, what is the point you're trying to make? What is the difference between solving it here and in the exam?
Here we can use any online calculators to find the minimum of that function. How to find that in exam? Like option 3 is we can know why option 3 is 0. But option 2 will be 0 when we know the value of the function is -1. So the loss will be -1 + 1 0 at W star B star.
Yeah. So one thing is, of course, in this question, what I expected is it's not about solving this entire equation, e to the power W square plus B square. Of course, in exam, we give you some kind of indirect hint if you really frame questions around this concept. But the thing is, exponential is actually a monotonic function, right?
Right.
So you have something on top of it. You are computing some numbers. So if you minimize this, will it be equivalent to minimizing this e to the power this W square plus B square?
Yes.
Right. So that's the hint. And of course, we don't really expect you to solve this by substituting. It may take some time to solve this W and B because kind of complicated if you incorporate this E into the picture. But we give you this visual stuff in this question just to ensure that we have this single minima, and also it looks like a bowl shape because of this W square and B square, and because we are taking exponential and it is going to be monotonic, and then there is a direct hint solving this. The minimum won't change for these two. Okay. That's an idea. So in exam we ensure that the computation won't be too long or too complex. We explore only the concepts.
So where I got confused is that's all fine, but W star B star if we substitute W star B star in original equation, it can have minimum that is less than -1, right? If we are not calculating, we are just we are just trying to estimate the minimum value.
Yeah.
So how will you proceed with this question if you saw it first?
Suppose that W star and B star. No, here we are mentioning that W star and B star are the values for which the function attains its minimum. Okay, so we have given you a function which has only one minimum. Okay, because it's W square plus B square passing through a monotonic function, so it must have only one minimum, right? So if I say W star and B star are minimum, right?
Right. Sir, but that minimum can be less than 0, right? Like not for this one, but for any e raised to x function, the minimum can be less than 0. Right?
Yeah, in general, it can be less than 0. So in such a case, we have to give you some hint.
Okay. So here, like if this question is asked in exam, more hints will be provided, right?
So if it is asked in the exam,
more hints regarding the minimum value.
Yeah. So of course.
Okay.
So if we frame this question in the exam, so of course, whenever we frame this question, any question, right, we first solve this from the scratch and see how long it takes and see how,
Okay.
I mean, what sort of hints they really need in order to figure out this step. So we keep all these things in mind because of this time constraint.
Okay. So what I did is I like first found out the value for that function on Wolfram alpha, and then I got it is to be -1, so I said option B is correct. Like would you solve it in any other way?
No, I actually framed this question by keeping these things in mind. I mean, this E is monotonic in the first sense, and we have only one absolute minimum, global minimum. So,
Right, sir, that is fine, right? What you're saying, but then if you are considering these two facts, then why will option A be wrong?
option A, what is that option A? So it says loss is not equal to 0. So far so W star and B star is not equal to 0. That's fine, right? Because what
Right,
is
but
the minimum
option
for
A is incorrect. So option A will not come.
option A won't come. So see, consider the surface. Am I confusing anything? W star the values then choose the correct statements. What I'm saying, correct statements, L of W star B star cannot be equal to 0, which means the loss cannot be 0 for this function. But in this case, it has to be 0.
Right. Why it has to be 0?
No, in this function, I'm adding +1, right? So that's
that
what
means that
see, if I don't add this +1, then this entire surface will move down in the y-axis. If we consider W and B, and the surface is plotted along the z-axis, and adding this constant actually moves this surface 1 unit above in the z-axis. So the minimum, the loss value cannot go, I mean, it is equal to 0. It has to be 0, right? Because W square B square has the minimum at 0, but since I'm negating it using this exponential stuff, it will push it. I mean, once you plot this, you can see that what happens if I add this +1 term to the graph.
No. Once we plot this, we get to know the minimum, that is -1 at 0, 0. But I'm asking, like, what if we don't have the tools to plot those? So how will you solve that question?
No, in such a case, maybe we will give you some hints. So from exam perspective, only thing I can say is that if we frame questions around some concepts, and we have to ensure, I mean, they don't have access to any kind of programming steps, right?
Okay.
And we have to give, even we might have mentioned 3D coordinate system with all 3 axes.
That would have made clear that the ball is at -1.
Yes. So if exam is completely different, the
questions
here.
Okay, then it's fine. Like, okay.
Okay, so the Next important network is ConNet. Of course, even if you don't know how to compute gradients for ConNet, that's absolutely fine. But if you are working out, if you are stuck at some point, please do ask. And the only thing that you have to know is how to compute number of parameters for a given convolutional neural networks. And also you should know what 1D convolution actually does to the number of parameters, okay, how it reduces number of parameters. So you solve, since I'm insisting on discounting number of parameters, there are many online, quizzes out there which help you to, ensure whether you understood how to calculate number of parameters for any convolution layers. Okay, please do solve some questions, some online from forums like Coursera or whatever that you choose, but try to work on a number of questions, okay, so that you are absolutely sure you know how to calculate number of parameters for convolutional neural network. Okay, that's the only important thing. So you should know how to compute convolution sum, and at least during forward propagation, you should know how to compute convolution sum and what max pooling actually does, and finally how these values of this padding and strides affects my output size. So all these things are necessary. If you don't know how to compute the gradient for the convolution, that's fine. Okay, yeah, so then we go into RNN. From CNN we just move into RNN. Of course, again from the examination perspective, you don't really need to know how to compute the gradients for you don't really need to know BPTT, back propagation through time. That's not required from the exam perspective, but you should know what is RNN, how forward propagation works in RNN, and what is sequence modeling, and which are the tasks. Given some n number of tasks, you should be in a position to figure out which task is suitable for RNN, and what is gradient, so the vanishing and exploding gradient problem, and how LSTM or any other variants fix this problem. So conceptually, you should know all these things. Okay, and finally the encoder decoder. Again, conceptually, you should know what is encoder and what is decoder. Okay, these are all the steps you should know for RNN and encoder decoder models. For transformers, you just try to distinguish how transformer is different from RNN based encoder decoder model. Both, we simply call it as encoder decoder models. We can either use RNN or transformer, and what is the difference, and how transformer actually, or what problem the transformer architecture is try to solve. What is the problem with RNN based encoder decoder model, and how transformer actually elevates that problem. Okay, so these are all the conceptual things you have to know about all these things. For transformer architecture, you need not to bother about calculating parameters. I don't think in the lecture we covered that. I think teacher has skipped over that part. So we are not focusing on counting parameters in transformer architecture. So the final thing is that as far as RNN and encoder decoder models are concerned, you should know what are RNN, what is sequence models and which problems are suitable for RNN, and how forward propagation works for RNN. Either it is, and also what is autoregressive. In RNN we have this concept of autoregression. I hope you may aware of it, but I'm just repeating it here. Okay, so I have some steps unfolded. So I feed in some input x1 and it produces some output y1. So when I say RNN is in autoregressive mode, then which means the output from the previous step is fed as input to the next step. Okay, so that is what we mean by autoregressive mode. Okay, and RNN can be used for different sequence modeling problem, where in each step you get an output, or only in the last step you get an output. Your input could be kind of, you feed in a single input but you get n number of outputs. So these are all different varieties of problems RNN can solve. But for all these concepts, you should know, you don't really need to bother about different varieties. Only thing is you should know how to compute things in forward propagation. Okay, that's all. Despite the type of problem, computing remains same. So you need not to bother about that one. Okay. So that's all for your end-term exam. So if you have any specific queries or if you have any doubts in RNN based models, please do ask.
Yes, sir. Sir, can you just give a quick review about selective write, selective read, and selective forget? Like as far as I can remember, like as far as I can understand, we do selective write for previous state. We do selective read for the input X, and then we do selective forget to combine both those two, right?
Yeah. So even I don't remember the formula. So only thing is by looking at the formula only I'm able to. I mean, conceptually you can. This single diagram summarizes everything. Okay. You can say so. Just for our sake of intuitive understanding, we call this as selective read, selective forgot, and selective write. Of course, just to make sense, how do we call this computation? So you can call this as selective read because that I'm taking some input, and then since it is a beginning stage, input stage, we call this as reading. And then before passing it to the next stage, we eliminate something, so we call that as forgetting. And then we incorporate new thing from the new input, so we call this as writing. Of course, these are for our purpose. Okay, so even I can't remember these formulas. So if you ask me all of a sudden write the formula for LSTM cell, I have no clue. Okay, so in such a case, what we do is in examination we give you these formulas. Okay, so we give you what these are all. Okay, the intermediate states and the hidden states, all these states. From that, of course, we don't ask you which one is selective read and which one is selective forget. Okay, that's not a matter there. So what matters is how the gradient propagates. Okay, so which path allows the gradient to flow. Okay, that these are all possible questions. I'm not saying these are all the questions that you will encounter in the end term, but if you frame questions around these concepts, these will be the questions. Okay, let's say you have LSTM cell and gradient is coming in. Let's say we have these gates, and let's say I'm using an sigmoid activate or either tanh or logistic activation function. It is explicitly here, and gradient is coming in. What happens, whether it will allow the gradient to pass to the next LSTM cell or it will block it, something like that. Okay, we don't really ask which component is actually selective read, which one is actually selective forget. Okay, you don't stick with this.
Okay. Okay, sir, but we are using the first selective write or the last one?
For which?
Like, let's say at a particular time step t,
Yeah.
to compute the value, we are using the selective write that is on the left hand side, right?
Yeah, so this is actually coming from the previous HT minus 1. All these are all previous cell. This is the input to the next cell. So this is a kind of loop. You can think of like I put one more loop here. So this is a repeating process.
Okay. So why don't we have the selective read at U instead of why don't we have selective read at U?
Yeah, you're right. In fact, there are even more than 40 to 40 varieties of LSTM and GRU cells. If you refer to the literatures, they replace all these. Okay, so whichever one that works best, they take that particular setup, and then that occupies the lecture. But you are free to experiment all these things. You can shift the place. You can put the selective read wherever you want in the input. If you want to put it on the input side, you can simply put it in the input side. The thing is that the block should be differentiable. As long as the block is differentiable, you can put that anywhere you want. But just to get some intuitive sense, of course, you can put it in the input side as well. There is no criterion that this should follow this step. That's why people are coming up with different types of kind of sometimes crazy architectures like residual nets. These are all kind of unexpected architectures. But the only thing that you have to keep it in mind, if it is differentiable, you can do that.
Okay. But we said in this lecture that selective read is for the input, right? With the IT gate.
Sorry, selective read is for?
input, right? We use IT gate to mask to have the weighted inputs.
Yes.
So like it should be at U, right? Because after we compute the sigma for the input U, we lose the like particular input.
No, selective read actually means it considers the current input as well as see. Okay. Okay, so before moving on, Himanshu, so let me ask others as well. So do they have any queries in this RNN so that they may drop off if they really want?
So
Okay,
what
Shalini.
will be the answer of the question that you have asked, that which path will allow to follow the gradient? And
Aditya, I got your voice getting break.
so wait. Sir, can you hear me now?
Yeah, it's quite better.
Okay, sir, you have asked the question that which path will allow to follow the gradient back. So what
Yes.
will be the answer this question, and how we will get the answer?
No, it's not which path. I mean, the main difference between a plain RNN and these memory cells, LSTM and GRU, these are memory cells, is that in RNN we have only one path, right? When you unfold the RNN structure, I don't know whether I'm able to write on this. So what do I mean by path? So when I move from one time step to the other time step, right? Okay. So essentially, I want to compute the weight updates for U and W, and if there are V, and also compute the gradient for this UWV, right? So you go for 25 time steps and then compute the loss and then back propagate all the way these 25 time steps and then accumulate the gradients and then update the weight. So this is the typical gradient updation rule for RNN, backprop through time. So when you really do back propagation, I mean start computing the gradients from the 25th time step and then to the 24th and then 23. Then you do really what really happens is that let's say I am sitting at time step T and then the next time step is xt plus 1 and then the previous one is xt minus 1. Okay, just using my own notation. I don't know, probably in the lecture they have used the same. Okay, so what I'm actually doing is I have to accumulate the gradients. I have to compute the gradients. Say for example I am computing gradient for W. Okay, so I have to compute the gradient for W at time step, say for example t plus 1. Okay, and then I have to back propagate. Okay, so I'm getting some gradients all the way from the loss, and then I'm passing this gradient through this time step and compute using that. I compute this one, and then I pass the same to the next time step. Okay, so if you look at the activation function used here, we use this not sigmoid, maybe tan h. Okay, since there is only one way that I can go from this cell, okay, a simple RNN cell to the next, I mean, it's again time steps, there is only one path, okay, and if that path gets saturated, then my gradient won't, I mean, I can't accumulate the gradient all the way till my 0th time step, okay. So that is the problem with plain RNL, and also sometimes people do truncated back propagation, but I don't want, you just note down. This is something practical because when you do 500 time steps, it is even quite difficult for LSTM, okay, to accumulate the gradient all the way up to 0th time step. Okay, so truncated backprop is there, that's fine. So in plain RNN, we provide only single path in all the time steps for gradients to flow across the time step. But in LSTM cells, okay, so you can see from these formulas, Okay, so we have these output gates. Maybe where can I start from? We have three different states. Let me see whether better diagram. This one.
No, last one.
Yeah.
This one only the best.
Yeah. So, okay. Oh, unfortunately, I can't write on this one. Can I use annotation tool? Do you see any annotation? I don't know why this Zoom call tool has this annotation tool.
Oh, you have Edge browser, then you open this in Edge browser or Edge browser, then you can annotate it. Just copy the link and open in the Edge browser. Microsoft
Is that
Edge.
possible?
Yeah. It's a default feature is there.
Okay, let me try to do that.
Right, sir. I also have like doubts in practice assignment question number 2 and question number 3.
Which week?
Week 10. Same.
Okay, give me a second. I don't know. Open. Okay, I open the Edge browser. Are you able to see the Edge browser?
No, sir.
No, it's PDF.
Okay. Are you hearing any sounds?
Like we can hear your voice.
No, sorry, not about sound. Kind of tracing some exceptions. Okay. Okay, which question, Himanshu?
2 and 3. Yeah, sir. In this question, it should be ST minus 1, right? Because when we are using order derivative, we first consider one as first, like we consider explicit and implicit derivatives, right? So the explicit will have v.
So it is actually at time step 4, right?
Right.
I mean, you are not even back propagating through t is equal to 3. You are computing with respect to time step 4, which means I think that is the last. Consider RNN time step 4.
But ST is there, right? So if ST is there, then it will be ordered derivative.
Okay, so I mean, it is with respect to V, right? Or ST.
Then it is with respect to ST.
With respect to ST, right?
Okay, state.
So you
Okay,
can zoom
okay.
inside. So you can click the downward arrow and then you can zoom inside the PDF.
Which downward arrow?
Beside recompiles, there is a recompile button, right? So beside
Okay.
yeah.
Oh my god, I don't know this feature.
Okay, so
Where is
not
that?
here. Okay, it's not here. So
after the compile, one download icon is there, I think. After that, yeah, the 2 icons after the icon.
Okay, yeah, it's not. I mean, it's fine. Do you want it to be readable, or do you have your own version at your side?
I have my own version. So
Okay.
But
Yeah.
this is correct, also, right? Because we are taking the log of yt, right? So log of y2 is going to be that it is going to be VST plus C in the denominator, right? And then we are going to take respect to ST. It's already a function. So we are going to write that O VST plus C. And as we are taking it respect to ST, C becomes 0 and it will come B. So it is going to minus B O divided by that.
Okay,
Right?
so
no, sir.
no.
So my doubt is it should be ST minus 1 in the upper term.
Which in this one?
Yeah, in this one, the last option is correct.
Sorry, you are talking about the option or the question itself?
So in this question, the last option is correct, right? Means the correct answer is the last option. The correct answer should have ST minus 1 instead of ST.
ST minus 1.
So if
No,
you
ST
zoom
minus
to,
1 where, I mean, we have ST in so many places in the
It's the
denominator
last
of
layer.
this.
So we are taking the last layer. It will be ST only. It will not ST minus 1.
but
One
when
thing,
you,
no, Himanshu, I think I hope I understand what you are pointing at. See, we
okay,
have this. It's like I have this component V here, right? I mean,
right,
V. How do I compute ST? I compute ST by considering W and the previous ST minus 1, right? Maybe, okay, I can draw big this one. It's like you can internally, I'm getting ST minus 1 and also some UXT something, all these stuffs. So I'm computing tan H of W ST minus 1, okay, and then plus this UXT, all these stuffs. Then I output something, right?
right,
So I call this as ST. I mean, state vector for the next time step, right? I feed
right.
this to the next times. I mean, use this in the next time step, and also if required, I take a branch out of it and then pass it through V, and then I compute loss, right?
No, I get this, but like when you try to do that mathematically, like when you try to find out that derivative, so
Dou L
in the white, yeah,
right?
in the YT, it is output of V ST plus C
I don't know where I missed it. VST,
plus C.
okay.
So, but the ST is like ST is not constant, right? It's dependent on ST minus 1, and that is dependent on ST minus 2. So
Yeah,
since
that
it's
is
an
true. Yes.
ordered, we will use order derivative, right?
No. See, for this computation, right? So you ignore this part. I'm just computing how loss changes with respect to my state vector ST, right? Of course, ST depends on ST minus 1. All these things are correct. But as far as loss at this time step is computed, my loss is directly connected to V and also this ST. Okay. So I'm actually asking you to compute dou L by dou ST. No, I got confused.
No, sir, can you just compute this derivative right now? It's like very simple.
Okay, so I reserve this. So
Also, sir, can you like as far as I can see, you have answers to all the practice assignment too. So like either you can
practice.
yeah. So like, do you have answers to practice assignments in the
Maybe
PDF?
I worked out, but I may not have entered in the kind of PDF.
Okay.
No, if I
Fine
had
then.
it in the PDF, I would have added it in
Okay, then
the
fine.
solution itself.
Fine. So here we are using output of VST plus C. So first we will
Okay.
like, if you can possible, you can like work out this derivative and then share it in the group.
Yeah, I do it, but okay. So it's not an issue. So you have two questions, right? So one is about regularization.
Two. Yeah.
And another one is this one. Okay, so I don't. Okay, I will work out and share it. Why it is the case?
Okay.
Can you go to question number 4 in this one, and where we need to find the total number of parameters. Same set, yeah.
Question number 4.
Okay.
Okay.
So, yeah, so we have given the 5 words, okay, and we have given 100 cross 1 that representation 1 not encoding, and further state vector has all 0 with 50 cross 1.
100 by 1 for the
That's
state.
okay.
Okay, that's correct. 50 by 1.
So how you solve it? That you are telling xt is 100, st is 500. U is 50 into 100. How we get U as a 50 into 100? This is my X.
Okay. Let me see what I really did. Okay, so what I need to do is I have ST, which is computed as WST minus 1 plus U into XT, right?
Right.
So what's my XT? It is 100 by 1. Am I right?
Right.
And then I have U, and then I have W. What's my ST? That's 50 by 1. What's that size?
50 by 1, right? ST is 50 by 1.
So I have to fix this size across the time step, right? So my ST minus 1 is also going to be 50 by 1.
Correct.
Right?
Okay, so make it to 50. So 50 something, you made it 50 cross 100. So that it become 50 cross 1 from the UXT, right?
Yeah, what's the size? Yeah, 50 by 100. So that's why it's 50 by 100.
And then W is going to be, again, we need to make it to 50 cross 1. So what is going to be W?
Yeah, that's 50 by 50.
Okay, 50 by 50 become 50 cross 1. Okay. And then how you are getting V? Okay, U and W, I understood. U and W.
So what is the 2? I mean, the output has to be 2, right?
Because it's, you are telling us just true and positive, true and false. So it's 2 and ST is 50, so it will become 2 cross 50. Okay. There I done the mistake. Okay.
Right. Also, sir, the input to RNN has to be a sequence, right?
Has to be as, no, it's not. I mean, sequence in the sense the sample should be dependent.
Yes, the
I don't-
output can be, the output can be or cannot be a sequence, but input has to be sequence, right? Means it has to be dependent.
No, why it should be as, I mean, it has to be dependent, but sequence in the sense, I don't know. So, for example, if you take an image, right, say 100 by 100, do you call it as a sequence or a single sample?
Okay, so it's a sample. I'm talking about question number 3. So the statement is false because just of output or input also plays a role.
Sorry, question number
3.
Yeah, that's what I meant by this. It's not necessarily a sequence in the sense, see, suppose if you take image captioning example, right?
Right.
The input is a static single sample, but the output is a sequence.
Okay. So both input and output cannot be a sequence. That's right.
See, RNS is so flexible. You are saying both output and input cannot be a sequence. No, it can
Yeah,
be a
if
sequence,
wanted
right?
to. No, that's also fine. But like the statement
No,
is false, right?
either output or input should be sequence.
Yeah,
If
so that's
both
what I
input
asked
and
in the
output
first place.
are not sequence, then RNN is not making any difference.
Okay, so input, let's say if the input is a sequence and output cannot be a sequence, that is right. We saw the example of stopwords, but can the vice versa be true?
Yeah, in this case, the input is not a sequence, but the output is sequence of words. The input is an image, but the output is, of course, it's a kind of encoder decoder model. So you can argue the input can, all the pixels can be related. There are kind of different problems that pose this image itself as a sequence. But in general, either the input or the output has to be a sequence for RNN. Both can
Okay.
be, but it is expected either input or the output, not necessarily both.
Okay.
Sir, when we use RNN and when we use CNN?
For which problem are you are asking in general?
Yeah, in general, just like sometimes we have image, sometimes we use as an input. Sometimes we have a sentence as an input. So when we use RNN,
Yeah,
and
so
then
the only thing that you have to figure out is, of course, that's just we talked about the sequential. We call this as a sequential model, right? So you consider a problem, say for example, classification problem. And if you are about to choose, should I use RNN or CNN? So the question is whether you want to pose this or cast this problem as a sequential modeling problem. Okay, you can use either two. I mean, either of CNN or RNN, it doesn't matter. But the thing is whether you consider the image as a sequence or a single sample with kind of no relation between two consecutive samples. Okay, so in CNN, we consider this entire image as a single kind of data point. Okay, it's not a sequence, it's a single image. It has no relationship between the consecutive inputs. Okay, that's where we use CNN. But you can cause the same problem and use the RNN by feeding in the image. I mean, by vectorizing this matrix stacking the rows of this matrix into a single vector and feed into the RNN. Okay, as a kind of one after the other, and then produces final output. It's a cat or dog. But of course, this is really unnecessary thing, but it is up to you. But it is how you cause this problem. Okay, whether you cause this as a sequential problem or just
so
kind of.
in question number 1, sir, it has been asked in question number 1.
Yeah. So for first question, given an image, generate a description. So description means it's going to be a sequence of words. So though my image is a single sample, but the input is single sample, the output is a description sequence. So RNN is okay. Given the historical weather data, forecast the weather. Of course, this is RNN. Given an image, find all objects in the image. Okay. So maybe this you might have thought of as a sequential problem. All objects in an image because there are n objects, right?
Yes.
Is that causing you trouble?
Yes, yes.
And that's what I'm realizing now. So it could be interpreted that way as well. But
Sir, but the order doesn't matter, right? So how
yeah,
can
that's
it
what
be
I'm
sequence?
thinking about. So at the fundamental or core level, what CNN is actually in fact modeling is this probability of y given x's, right? This conditional probability that might not fit for this example because it is not conditioned on any of these previous outputs. So whether finding the first object has influence on finding the next object. So in that argument, we can say this is RNN is not suitable for this problem. But I don't. I mean, in fact, when I given you this option, I didn't realize that this is a sequence, all objects in the image.
Maybe
Okay,
if the question is a given of set of images, then it can be an RNN. If you're given set of images, find all the object in the image, can be an RNN.
That's also not a RNN problem, right? Because when you model this, what RNN does is this one, conditional probability. So if you have n number of objects, right? So finding the first object influences the probability of the next object. And then these together influences the probability of the next object.
No, like video when we are doing that previous image has some reference of the next image.
Video you can see, yeah.
That set of image means I'm talking about a video. Okay, then it can be a video.
Yeah, the set of images are correlated in the sense, right?
Right.
It has some influence. Thanks, Aditya. I have to rewrite that question, maybe, or I have to give some sort of information.
Can you come to question number 4 again, sir? One more thing. So here you got, okay, the 50 cross 100. So U has a bias of 100, W has a bias of 50. Now B has a bias of 50. How you are getting this 2? From where this 2 is coming?
The output neurons?
Output neuron will have a bias, but we are passing as a V, right? Okay, V, no. Okay.
So what is the size of V, by the way? It's 2 by 50, right?
Yeah, 2 by 50.
So which means I essentially have 2 neurons in the output layer. But I think you can also say it is positive negative by using 1 neuron.
No, I'm because you written positive or negative, so it can be only one. Bias is not needed, maybe.
No, bias is still required because you have to add 1 bias there.
Sorry, yeah, one bias is needed, right? One bias is needed.
Yeah, so I think when I framed this question, somehow I mapped this to 2.
Okay, one more thing. Here we return this compose of 5 words. So the number of parameter doesn't depend whatever the number of words we are going to pass, right? It's not depending or changing its parameter, right? Because it's just
Yeah. So that's why we go for RNN, right? I mean, in the beginning of the lecture, we discussed various way of tackling this sequential problem. So if you make it dependent on number of words, then the parameter, I mean, the entire function depends on the number of words, therefore the parameter. So there is no way of kind of learning this W because it keeps changing for each sentence.
no. What I am telling this XT we are passing, for example, the first time. So first time we are like we have 5 words. So first time we are passing 100 cross 1 parameter means as in one hot cutting. Then it is going and I'm getting some output, and then it is coming as an auto recursive to the second one, that is my X2. So again we are passing 100 cross 1, right?
Yeah.
So that is not going to be at this 100 as we are passing it, or it will
No,
be just
the parameter won't get modified. You are sharing the same value. The U remains same across the time steps, right? So it's not changing.
okay. We need to find the UWV, not the X or ST.
Yeah, it's like even if you have fully connected layer, feed forward neural network, right? So it's like we have feed forward neural network with one hidden layer, but the parameters of the hidden layers remain same.
Right. Yeah, correct. Okay, understood. Thank you.
Also, sir, does the NTM have like 20 marks questions?
No.
Please do not do.
No, we actually, remove this dependency between answers and also giving high weightage to, and of course there are no questions which actually requires two long computations where we need to give high marks. So in the quiz 2 question, computing the gradient for the convolution layer really takes time. So that's why we have no other way other than giving high weight points for that particular question. Because if you work out, it takes at least 10 minutes. So it depends on, so the mark is awarded based on the time it takes to solve that particular question. And of course, in the end term, we don't have any such questions.
The
No
problem is
questions
that it is
have,
actually an NAT. If you do a small mistake, the entire 10 marks gone. That's the problem. Even we are doing a correct calculation, maybe somewhere doing calculation we have done something wrong, and then it can go wrong.
yeah. So what we should have done is we should have break down that 10 mark question into 5 intermediate steps, and then we should have evaluated. So, and also we anticipated,
But the paper is of 50 marks, right? So we get 100 marks total. So
yes.
the 10 marks question becomes a 20 marks question.
Yeah, I understand. Yes, that's why actually we manually did this moderation. The answer cannot deviate much, but of course, when number of steps are, kind of, if it is a lengthy calculation, the mistake can happen at any step, so it can lead to two different answers. So yes, we should have divided that entire steps into 5 individual questions. Maybe that might help someone. Okay, so Himansh, I work out and come back to you on that question.
Right.
I post it in the group.
Okay. Sir, I can post more doubts in the group, right? Or in a personal chat to you.
Yeah, you post it in the group or in the chat. So So I try to answer those. Maybe I take some time because I engaged with some other works. I try to give some priority to whatever the question posted in the group and work on it.
Okay. No, it's okay. We still have 2 more days.
Okay.
Thank you for this
Thank you.
session.
Thank you. Thanks for time.
Thank
Yeah.
you, sir.
All the best for your interim exam. So don't worry. Just work out GA, PA, and then quiz questions. That will be more than enough. Okay. Bye. Bye, everyone. Thanks
Bye
for
bye.
joining.
Thank you. Thank you.
Bye, sir.